It's just really misty. Yeah. No, it's not. There was a blizzard like yeah, I was looking. Yeah, like it's April. It's not supposed to be. I was like trying to figure out where I was like on the weekends I like to go climbing. I was trying to figure out where I wanted to go, and like everywhere it's like 10 inches of snow. Yeah. Except like in Rhode Island. Like the rest of New England is like so much snow. So we escaped that at least.
It's 6 inches.
Okay, so last time we ended with Euler's formula, which said the following. So it said, so let's let G be a plane graph with n vertices, e edges, and f faces. So yeah, maybe I should explain this. So like last time we said that a graph was planar if we could draw it in the plane with no edge crossings. And then the faces are the connected regions of the plane, the maximal connected regions of the plane left behind if you removed the graph. So then let's let f be the number of those faces, and then we have n vertices and e edges. Then we prove that the following formula was satisfied. And it is n minus e plus f is equal to 2. Okay, so today we're going to use this formula to first prove some inequalities that basically sort of clarify the intuitive idea that we could have too many edges for the graph to be planar, right? Because if it has tons of edges, then you're always going to have crossings no matter how you draw the graph. So let's make that precise. So we have a theorem. It says if G is a simple, so no loops or multiple edges, planar graph with at least 3 vertices, then E of G is less than or equal to 3 times the number of vertices of G minus 6. And then a second statement is if G is triangle free, then E of G is less than or equal to 2n of G minus 4. So this is going to be like a corollary of Euler's formula. So we're going to have to use that in the proof. So let's prove this theorem. First, other questions about the statement? Okay, so the first observation is that it suffices to only consider, so for Euler's formula, we, oh shoot, I think sorry, in my recap of Euler's formula, I left out a condition. So we need this to be connected. And I think last time we also said it needs to be non-empty. Okay, so in order to apply Euler's formula, we first need to reduce to the case where we're looking at connected graphs. So the first observation is that it suffices to consider connected graphs. Because otherwise we could just add edges in order to make them connected. So let's say I had just in this example, 2 connected components, then I could just take a vertex from each one and add an edge there. And now I have a connected graph. And if the inequalities hold, so this puts an upper bound on the number of edges. If these inequalities hold for this graph, then they also hold for the graph where I've deleted this edge and I have now fewer edges. Okay, is it okay? So now our goal, so we want to get a relationship between n of G and E of G, and we want to use Euler's formula. So we need to get rid of F somehow. So our goal, oops, is to somehow eliminate F in Euler's formula to get a relationship between E of G and N of G. Okay, so for our first case, we're considering simple planar graphs with at least 3 vertices. So what can I say about the number of edges in every face? Can I make some claim about how many edges are in every face?
For planar graphs, are we allowed to have two, for simple planar graphs, are we allowed to have two edges between this, like, two vertices, or?
No, because for simple graphs, we've disallowed multiple edges, yeah.
So then 3?
Yeah, so every face has at least 3 edges in its boundary. So let's let okay, well, so recall from last time we had this thing called the length of a face, which was the number of edges in its boundary, possibly counted with multiplicity if you had like a leaf. So we had this equation that said that 2 times the number of edges was equal to the sum of the lengths of the faces. And now we're saying that this is greater than or equal to 3 times the total number of faces, right? Because I'm going to count up the length of each face, and we just said that the length of each face had to be at least 3. Okay, so then now we're gonna plug in Euler's formula. So that, just rearranging that, it tells me that F is equal to 2 plus E minus N. So then I'm just going to plug that into this inequality. So I get 2 times E is greater than or equal to 3 times F, which is equal to 3 times 2 plus E minus N. Okay, I'll expand this. So 2E is equal to 6 plus 3E minus 3N. Okay, and what was the, oops, sorry, this should be a greater than or equal to. So then we have, let's put all the E's to one side and everything else to the other side. So we have 3N minus 6 is greater than or equal to E. Hopefully that's what we wanted to prove. Yes. Okay, are there questions? Yeah.
Can you just explain quickly again why every face has at least 3 edges?
Yes. Okay, so for a moment, let's ignore the unbounded face on the outside of the graph. So every bounded face, so we have at least 3 vertices. So if you have a bounded face, it has to, basically, it could not be something like that because we've disallowed. The graph has to be a simple graph. And then for the unbounded face, I think it's the same thing, right? We have at least 3 vertices. So it could be a tree, but then we're counting each edge twice. So it would have 4. Yeah. Are there other questions? Okay, so then for the second part, so we also wanted to prove an inequality about if this is triangle free. So for that, I'm just going to modify the argument. So maybe I'll just write that in parallel over here. So if G is triangle free, then what is the new version of this inequality? Yeah. Yeah, so this is gonna be 2 times E is greater than or equal to 4F. Because every face is gonna have now at least 4 edges. So then, so yeah, so then we'll just repeat this. So we get 2E is greater than or equal to 4 times 2 plus E minus N, which is 8 plus 4E minus 4N. And then rearranging that, we're gonna get 4N minus 8 is greater than or equal to 2E. So then 2N minus 4 is greater than or equal to E. And is that what we wanted to prove? Yes. So then that completes the proof. Okay, are there questions? Okay, so then as an example, so at the beginning of the day, yesterday, we saw kind of a complicated proof, not that complicated, but still a little bit complicated, that K5 and K3 were not planar. So now as an example of this theorem, I'll have you guys prove that K5 and K3 are not planar. Okay, so let's go ahead and let's prove this. So for K5, how many edges and vertices? Yeah, so we have 10 edges and 5 vertices. So then 3 times 5 minus 6 is 9, which is less than or equal to the number of edges. So that means that this can't be planar. Because it violates this inequality. Okay, and then what about K3,3? Yeah,
9 edges, 6 verses.
yeah, and then so what happens if you try to do this inequality?
It's fine if you do that one, so you need to do the other one.
Yeah, so I think if you compute this, it passes the test, but K3,3 is also triangle free. So we have this additional one. So let's check that one. So we get 2 times, oops, and this should be an n. 2 times 6 minus 4, which is 8. And that is less than or equal to 9, which is the number of edges. So this is also not planar. So basically, like, my interpretation of these two things is that, so this puts an upper bound on the number of edges that you can have in a planar graph. And so you can sort of see that K5 and K3,3 have too many edges to be planar. Okay, so let's see a definition sort of related to this. Okay, so we're gonna say a maximal planar graph is a simple planar graph that is not a spanning subgraph of another planar graph. So meaning I cannot add any edges to it and have it still be planar. So as soon as you start adding edges, it will no longer be planar. And then the second definition, triangulation is a simple plane graph where every face boundary is a 3 cycle. So I guess with these inequalities, right, we've kind of seen that if you're triangle free, then you get a tighter bound on the number of edges. So sort of having as many triangles as possible will give you, like, this is just intuitively as many edges as you could have. It's like if you had some face that wasn't a triangle, you can add an edge to that and it would still be a planar graph. So we're gonna make that more precise. So we're gonna like sort of relate these two definitions, but then also like what happens when this is equality here. So we have the following proposition. So it says for a simple n vertex plane graph, G, the following are equivalent. So the first one is that G has 3n minus 6 edges. So that inequality is an equality, the one that we proved in the previous theorem. And then second, G is a triangulation. And 3, G is a maximal plane graph. By the way, I didn't draw any examples of these things. Would that help? Maybe now I'll just draw an example over here. So like, let's throw down some vertices. Okay, so to make this a triangulation, I want the boundary of every face to be a 3 cycle. So I'm gonna have just fill this in kind of randomly with triangles. But then I also need the like the big face on the outside to also okay, the way that I did this was like bad. Starting over. So if I want to make a triangulation, the easiest way to draw that is just going to be to put a big triangular face on the outside and then have whatever vertices, whatever other vertices I want on the inside. Okay, so this is a triangulation. Okay, and then we could also check that it satisfies this if we wanted to. And I think it kind of makes sense that this is going to be a maximal plane graph because there's not really any way to add an edge without conflicting something that we already have written there. Okay, does the example help or are there questions? Okay, so let's prove this. let's start with the equivalence of 1 and 2. And I'm gonna give you a few minutes to think about a possible proof of why these two are equivalent, and then we'll discuss. Okay, does anyone have an argument for the equivalence of 1 and 2? Yeah,
For the inequality we have above, the equality is like if and only if we only have, triangular faces.
yeah, exactly. So like going back to this part of the previous proof. So this thing is gonna be an equality only when this is an equality. And this happens when every face has exactly 3 edges in its boundary. So I'll write something. Okay, so the previous proof shows that having 2n minus 6 edges in a plane graph is equivalent to two E equals 3F, which only occurs if and only if every face is a 3 cycle. Okay, are there questions about that part? Okay, so then let's do the equivalence of 2 and 3. So again, I'll give you a few minutes to think about it, and then we'll talk about the proof. Okay, does someone have an argument for why 2 and 3 are equivalent? Yeah,
Well, it's maybe a bit like too simple, but like I said that like if two is equivalent to one, you have to, if you add an edge, then the no longer satisfies like equality or like the inequality.
mm-hmm,
Or like you have to like E of G is less than or equal to 3 of 10
yeah,
times 6, so you add edge it.
so then. Okay, then what about 3 implies 2? Okay, so let me just, I'll write that down quickly. So, okay, so if G is a triangulation. Then G has, oh, I never like wrote down this full statement. Okay, it has that many edges. So if we add an edge, it violates the inequality. Um, and so that means that it's maximal planar. Okay, so that was 2 implies 3. So then what about 3 implies 2? Yeah.
You can do this one by like contrapositive, suppose that G is not a triangulation.
Mm-hmm.
And there's a face with more than 3 edges, or there's a face that's like surrounded by more than 3 cycle. So take 2 non-adjacent vertices, now an edge between them going through the face.
Yeah. Okay, so if G is not a triangulation, so we're doing this by contrapositive. So if G is not a triangulation, then some face has more than 3 edges. So there is an edge. To this face. So then G is not maximal planar. Okay, are there questions? Okay, so what we are now going to do is work towards a characterization of plane graphs. So our goal is characterize plane graphs. So make a statement of the form G is planar if and only if something. So let's start with a proposition. So, okay, so the two like examples, the key examples of non-planar graphs that we know are K5 and K33. So we're gonna make the following observation, and we'll prove this, which is that if I have a K5 or a K33 sitting somewhere in the graph, then that is gonna be a problem. Like that is going to make me not be planar. So here's a proposition. So it says that if a graph G has a subgraph that is a subdivision of K5 or K33, then G is not planar. And this was like from a while ago. So what is a subdivision? So that's if I take an edge and just replace it with a path that might have more vertices along it. Or another way to think about this is like if you have an edge, you're just adding more vertices into that edge. Okay, so let's prove this. Oops. So first, let's observe that every subgraph of a planar graph is also planar. Does this make sense? So if I start deleting edges, that will still, the graph will still be planar. So then it suffices to show that just subdivisions of K5 and K33 are non-planar. Okay, does this make sense? So then let's just observe that subdividing edges is not going to affect planarity. So why is that? If I have some graph and I have an embedding of it, then if the graph is planar, then I can use that same embedding, just adding a vertex wherever the edge is subdivided to obtain a planar embedding of the subdivided graph. And vice versa, like if I have a planar embedding of the subdivided graph, then I can just erase the vertices, the extra vertices, and that will give me a planar embedding of the original graph. So G has a planar embedding if and only if subdivided G has a planar embedding. Okay, does it make sense? Are there questions? Okay, so we know that having a subgraph that's a subdivision of K55 or K33 is illegal. And it turns out that this is actually enough. So this is something called Kuratowski's theorem. So it says a graph is planar if and only if it does not contain a subdivision of K5 or K33. Okay, is the statement clear? Okay, so the proof of this is extremely long and complicated. So, and it also requires like some additional technology that has nothing to do with graph theory. So what I've tried to do is break this down into what I think are like statements that are like at least believable, like, okay, maybe this requires proof, but like I find this like viable. So that's what I'm gonna try and do, is just present the proof, not at the full level of detail, because that would probably take like multiple class days, but just like go through the proof and sort of say which, like just break it down into statements that I think are believable, and just say like when additional proof is required. And all of it is like presented in full detail in the book as well. So if there's something that I say here that I'm like, oh, this is like a lemma that's proved, then you can, like, if you're curious, you can go and look. So here's the proof sketch. So there's sort of two parts. Okay, so part one is to show that a minimal non-planar graph that does not contain one of these subdivided K5 or K33s has to be 3 connected. So show that a minimal non-planar graph not containing so I'm gonna call this Kuratowski subgraph. So this is just whenever you have a subgraph that is a subdivision of K5 or K33. So a minimal non-planar graph, which does not contain one of these things, is 3 connected. And then part 2 show that every 3 connected graph with no Kuratowski subgraph is actually planar. Okay, so like recapping the logic here. So we already proved that if you are planar, you do not contain a Kuratowski subgraph. That was the previous result. So now we need to prove that if you do not contain one of these, then you're planar. So step 1, show that if you don't have one of these and you're minimally non-planar, then you have to be 3 connected. And then show that if you're 3 connected and you have this, then you have to be planar. Okay, so those are like the steps. So then, does that make sense? Are there questions? Yeah.
So when it says non-planar, is it like we're not assuming it's planar or we're saying it's not planar?
We're saying it's not planar. So yeah, okay, so let's like go through, let's like map out the argument. So if I'm a graph that does not contain a subdivision of K5 or K33, let's suppose this thing is non-planar, then it contains a minimal non-planar subgraph. That thing has to be 3 connected. But then by part 2, it turns out that every 3 connected with this property has to actually be planar. So that gives a contradiction to it being non-planar. Should I say that again?
So it's like, suppose that you have a non-planar subgraph, not containing the Kuratowski subgraph,
Yeah,
then it's 3 connected. But then part 2, since it's 3 connected,
it's planar.
Yeah.
Yeah. Does that make sense? Okay, so then I'm gonna map out now, like, how do we prove each of these 2 parts? Now that like we understand the general structure of the argument. So for the first part, here's like the steps. So there's one lemma. So we want to prove that a minimal non-planar graph not containing a Kuratowski subgraph is 3 connected. So the lemma says if G is a graph with fewest edges among all non-planar graphs without Kuratowski subgraphs, then G is 3 connected. Okay, so here are the steps to prove this. So the first observation is that, okay, right. So we want to prove it's 3 connected. So we need to prove that it's connected, and we need to prove that there's no cut vertex. And that there's no separating 2 set. So that's like what the steps are going to be. So connected. No cut vertex. And then no separating 2 set. Okay, so then why is it connected? Yeah,
You just say it's connected by minimality, because if it's if it's disconnected and non-planar, one of its connected components must be non-planar, and that one also goes in containing Kuratowski subgraph, so it would be more minimal.
yeah, exactly. So, by, okay, right. So if there were multiple components, each component is a subgraph of this minimally non-planar thing. So that means that each of the components has to be planar. And this contradicts that G was planar. Okay, so why 2 connected? So why do I not have a cut vertex? The reasoning is pretty similar to the connected case. So if I have, let's suppose I have a cut vertex. Let's draw a picture of this. So I have like some vertex with a bunch of edges coming out. And then I have two connected components. Then again, by the minimality, each of these components is planar. And then I can piece together the two planar embeddings, or I guess there could be more than two, but however many connected components there are, I could piece together those planar embeddings to get a planar embedding of all of G. So maybe let's do an example. So let's say I had one component like this, another component over here. Okay, and then let's say I had like this cut vertex in the middle that's connected to like all of the other vertices. No, I'm skeptical now because I feel like I can't connect this. Just look at the book really quick.
The central in a square, and you move the central vertex like outside the square, then move all the edges. Wait.
Oh, I see what you're saying. I just drew this badly. So okay, wait, what was the graph I had? So and then the other vertex. But now I can't connect like that. I'm confused.
Then you just sort of flip the square. But then if you wanted to get to the two opposite corners of the square and that central vertex would be annoying.
I feel like the point here is somehow we have to use the fact that there's no Kuratowski subgraph. Because like this is probably creating like a K4 or something, hold on. I'm just gonna look really quick.
Sort of same like minimality argument sort of works here.
Okay,
Like, you have all your disconnected components, they're smaller, therefore they must be planar. And therefore, what's making them non-planar is like the added edges to the cut vertex. But then you have a subgraph containing just the cut vertex, one of the planar components, and all of the edges connecting those. And then
Yes.
it's smaller.
yes, okay. Okay, so this is, yeah, I think that does fix it because, okay, so let's just stare at this subgraph of G. Since G is minimal non-planar, that means that this subgraph has to be planar. Like the chunk of including, so not just the component, but the component together with the edges to that central vertex. So that has to be planar. Okay, so this, I need to be more precise here. So piece together. Okay, let's go back to this. Each of the subgraphs, which look like connected component together with central vertex and edges to that vertex. So edges to the cut vertex. Okay, so this situation that I drew here is like not possible. Okay, does it make sense? Are there questions? Okay, so then the last case is to prove that this is 3 connected, is that we have to argue that there's no separating 2 set. So let's suppose there is a separating 2 set X, Y. Then there's a lemma in the book that proves that some component of G minus XY together with the edge XY and edges from XY to the component. Okay, so let me draw a picture. So this graph is non-planar, is the lemma. Okay, so here's my separating set XY, and then I have some component over here. Some component over here. So the graph under consideration is this subgraph. So the set XY together with that edge whether or not this edge exists in the graph. So the edge XY may or may not exist, but we're gonna consider the graph consisting of one connected component together with this edge, together with any edges going between X, Y, and the component. So it says that this thing has to be non-planar. And then by so this is like some result that has to be proved. And then if we assume this is true, then by the minimality of G, this must contain a Kuratowski subgraph. So okay, so then what happens if this edge does not actually exist in G? Then we could just replace it by a path that goes through the other component. So okay, so like going back, if G does have the edge XY, then this graph by the lemma has a Kuratowski subgraph, which is a contradiction. If this edge does not exist, then in this graph, I'll just replace it by some path going through the other component. And then that tells me that this thing now has to have a Kuratowski subgraph. And that contradicts there being a separating two set. Okay, so that was the sketch of part 1. So going back, so we had this theorem that gives a characterization for when something is planar. The proof is in 2 parts, and we've now sketched part 1, and I would say we've proved it up to this lemma that I just quoted for this, like, this portion. Okay, part 2 is worse in terms of like number of things needed to be proved. So it's gonna get, so this, the second part's gonna get sketchier. So sketchier proof sketch of part 2. And let's go back to, I forgot what the statement of part 2 was. Okay, so for part 2, we want to show that every 3 connected graph with no Kuratowski subgraph is planar. Right, okay, so we've now proved that the things that we're worried about are all 3 connected, and so now we have this like extra assumption. Okay, so we want to show every 3 connected graph with no Kuratowski subgraph is planar. Okay, so they actually prove something stronger, which is we're gonna replace planar by that this thing has what's called a convex embedding. With no 3 vertices lying on a line. And convex just means that every face boundary is a convex polyhedron. And the proof goes by induction. So the base case is for whenever n is less than or equal to 4. And the only 3 connected graph in this case is K4, which has the desired embedding. Okay, and then for the induction step, they prove that there is an edge that you can contract. So there is an E such that G contract E is 3 connected. So this is a lemma. And then another lemma, G contract E has no Kuratowski subgraph. And then by the inductive hypothesis, we get a convex embedding of G contract E with no 3 vertices lying on a line. So G contract E has the desired embedding. This is by inductive hypothesis. Okay, and then sort of the last bit is that now we need to prove that in this embedding, we can expand the edge. So we might have some things coming out of here, and we need to argue that there's a way to expand that edge without introducing crossings among the edges coming out of it. And basically, the cases where you have introduced crossings, if you go through it, they end up implying the existence of Kuratowski subgraphs. So there's like an argument to show that like when you expand it, it expands nicely. So possible to expand by additional argument. Okay, so that's the proof sketch. So you have a problem set due tomorrow, and then also the midterm due next Friday, and the midterm is posted, so you can already get started on it if you like. And other than that, I hope you have a good weekend.